Welcome back, ladies and gentlemen. In this video, we are opening up a brand new section. We're going to be talking about de Moivre's theorem. Throughout this section, there's a lot of parts in this 6.6 section. So we have an entire goal of being able to represent complex numbers in the complex plane. Yes, there are a way to graph complex numbers. They're not exactly as imaginary as we think. And we're going to write them in polar form. Then we're also going to be able to use polar form to simplify some algebraic expressions using complex numbers. But that's kind of its big entirety. So the goal for this specific video is 1, I'm going to define what the complex plane is. All right. 2, I'm going to go ahead and talk about how we have another name for absolute value called modulus, and how that actually represents something that we've talked about in vectors as well. And then we are going to plot some numbers on the complex plane. So those are the 3 things that we're going to look at in this video. So first and foremost, let's talk about the imaginary plane, or the complex plane. The complex plane, and it's a little bit blurry here, so I'm going to go ahead and rewrite these. The complex plane is made up of a horizontal real axis and a vertical imaginary axis. So all your real numbers are on that horizontal axis, and all your vertical numbers are the imaginary axis. And so basically, when we see a complex number like a plus bi, we can take the horizontal component as the a, the real number, and then the coefficient in front of I is going to be the imaginary axis, which makes sense to us. And then you're going to plot it exactly as you normally would any other kind of positive or negative value on an xy axis. So let's take a look at an example. If I asked you guys to go ahead and do 2 plus 3i, well, 2 plus 3i is over 1, 2 units on the real axis, and it's up 1, 2, 3 units on the imaginary axis. And so you would have a point there at 2 plus 3i, and then usually we kind of denote complex numbers as z, so I'm just going to call it z. There's a point z right there at 2 plus 3i. So why is this kind of important? Well, if you kind of imagine what we've talked about so far, you know, the xy axis is truly in pre-calculus becoming so much more than just a bunch of ordered pairs, right? From ordered pairs to what we talked about in parametric equations, what we've dove majority on in our trig functions and using them as relationships between cosine and sine and tangent and the hypotenuse and all these kind of things. Like, it's really becoming so much more than I think we ever really expected when we kind of began this math journey, and that doesn't really stop here with our imaginary numbers. And what we end up actually seeing is that this concept of these reference triangles that we made with the unit circle are really kind of still going to continue on. And so if you kind of imagine for a sec that, you know, we had 2 units, right, that we went to the right, and then we really had 3 units that we went up. Well, we can kind of create, yet again, another reference triangle, or another triangle, right? Triangle is really all that it is, right? To kind of make some connections here. And what we end up finding out is actually when we go ahead, and if you remember when we were finding vectors, right? If I wanted to find the length, the size of this vector, I'd find the magnitude, right? So that would give me a length or a size to this vector right here. Well, similarly, when we talked about it with our trig functions, that was the hypotenuse of the reference, triangles, and that really was the r. That was the part of the ratios for cosine, sine, and tangent. Well, we're just going to add something else to it now. We're going to find the exact same thing, but now when I'm talking about finding this r right here, r is now going to be looking like the absolute value of z, but we're not going to call it the absolute value. It's actually called the modulus, and the modulus is literally just the distance from the origin to a point. And so ultimately, I can always find that modulus by basically doing the same thing as I did by finding the magnitude of our vectors. So in this case, it would be 2 squared plus 3 squared, and you'd end up getting the square root of 4 plus 9, which is really the square root of 13. And now you could use that same information for a variety of different things, and then we're going to use it specifically with imaginary or complex numbers in this, situation, in this section that we're in. But now we've talked about basic absolute value, right? The distance away from 0. Then we talked about the modulus now, which is the distance away from the origin, which makes perfect sense. And then we also talked about it in terms of the reference triangle being the hypotenuse of the reference triangle. And we talked about it being as the magnitude of a vector. All of them are really basically the same thing. They are just called something different depending on the situation that you're in and depending on the context of the math that we are discussing. So let's go ahead and continue with a little bit of plotting complex numbers and kind of just show one little extra tidbit to it. So it says we want to plot the following. 1 plus 3i, so positive 1, and 1, 2, 3i. So that would be my point U right there at 1 plus 3i. So there's our real axis, and here is our imaginary axis. We want to plot 2 minus I, so 1, 2, and minus I would be down there. So there's V. We want to add U plus V. Well, U plus V is literally adding the two together. So I would have 1 plus 3i plus 2 minus I. So that means 1 plus 2 is 3, and 3 minus 1 is 2i. Well, positive 2i. So 1, 2, and 3, and 2i is right here. So there would be U plus V. And then there's our origin. And it says, plot these 3 points with the origin and ask if it's a parallelogram. So you might be wondering, well, why the heck does a parallelogram come on into play? Well, if you remember back to when we first started talking about vectors, right, we could say that you could take the sum of these two vectors and they would end up forming a parallelogram. So you have a couple options. One, you can literally find the slope of the opposite sides, find out that they're parallel, and go with from that. You could also find the distance formula between all of these points, and if the opposite sides are congruent, then it's a parallelogram. All your basic things from geometry, you can do all those things as well too. I'm going to kind of just show it in terms of what we know about vectors, because basically what's going to happen is if the vector form ends up equaling the same sum as our complex form, then we do have ourselves a parallelogram. Because if I were to do the exact same thing in vector form, as you can see, we have 1 and 1, 2, 3. So 1, 3. So now I'm saying that this is the vector 1, 3. And then I have 2 minus 1. So I have negative 1 there. So here is the vector 2 minus 1. Basically what we are saying is if I added these two vectors together, 1, 3, and 2, negative 1, are we going to end up getting the 3 plus 2i? And obviously, as you can see here, we do get 3, 2. And so we end up putting ourselves in the same situation that we were before. And when you add those two vectors, as I said, it should represent a parallelogram. It was one of the first things we learned in our vector talk. And that does form a parallelogram. Therefore, it was the same values as it was with the complex plane. So yes, it is a parallelogram for sure.